Hi, it's problems from AMC-8, wonderful American contest. So I picked 3 problems from AMC-8 exam, and we will discuss them today. So it's a problem number 18 from 2015 exam. An arithmetic sequence is a sequence in which each term after the first is obtained by adding a constant to the previous term. So we all know that. Then they give an example. It's a whole lecture about arithmetic sequences. Each row and each column in this 5 by 5 array is an arithmetic sequence with 5 terms. The square in the center is labeled x as shown. What is the value of x? Okay, so my strategy is to fill in the first row. So this number will be known. Then I can fill in the last row. Imagine this number is known. Then I can fill in this column using my knowledge of arithmetic sequences. Okay, that's my strategy. Okay, let's see what is happening at the first row. Each time I jump to the next square, I have to add the same number. Let's go with D. So in order to get from 1 to 25, I add 4. 4 values of D. The result is 25. So I'm good at arithmetics. It's a key to success on AMC, of course. So I do not stuck with the solution D equals 6 each time I move to the next square. I have to add 6. Let's do it. 7, 13, 19, and 25. That works perfectly. Then let's do the same with the last row. Okay, but instead of using D, I have to use another letter. So we start with 17, and each time we add, let's say, P. So after 4 P's, we are at 81. So move 17 to the other side. Is 64 divided by 4. P is 16. So I add 16 every time. So it's 33. It's 49. And it's 65. Okay. Then, according to my strategy, I consider this column. We start with 13. We add 4, let's say, K. The result is 49. Let's solve it quickly. 36 divided by 4, it's 9. So let's add 9. 22, 31. That's my answer. Okay. To have a nice picture, we add 9 one more time. It's 40, 40, 49. Okay, that's it. The 31, I think it isn't a very difficult problem, but it's so valuable for grade 8 or grade 7 schoolboys and schoolgirls. So, wonderful question. Let's move on. Okay, it's the same exam of 2015, but problem number 20. Ralph went to the store and bought 12 pairs of socks for a total of $24. Some of the socks he bought cost $1 a pair. Some of the socks he bought cost $3 a pair, more expensive, and some cost $4 a pair, okay, the most expensive. If he bought at least 1 pair of each type, okay, this is an important piece of information. How many pairs of $1 socks did Ralph buy? Okay, I feel that I need some letters to denote unknowns. So X is the number of $1 pairs. $1 pairs. Y is the number of $3 pairs. And Z is the number of $4 pairs. Okay. So on the actual exam, there is no need to write this way because you can store this information in your mind. So having these letters and designations, we can start setting up equations. So the first equation comes from the first sentence. So there were 12 pairs of socks in total. So x plus y plus z is equal to 12. And the second equation is about money. So x pairs, $1 each. So I multiply the number of pairs by the price of each pair, plus y pairs, $3 each, z pairs, $4 each, and the total is 24. So you can see a lack of equations because there are only 2 equations with 3 unknowns. But do not underestimate the condition that x, y, and z are positive integers greater than or equal to 1. So this it plays a role of another equation. So it contains no less information than a whole equation. So when I look at these 2 equations, I still don't like them because there are too many letters involved. So in order to reduce the number of letters, I subtract the first equation from the second. So let's do it termwise. X and x disappear. 3y minus y is 2y. 4z minus z is 3z. It's equal to 24 minus 12. It's 12. Look, this equation is much more convenient because it contains less number of letters. So now I can just guess the value of y and the value of z because they are positive integers bigger than or equal to 1. So the number on the right hand side isn't as big as it could be. So 12 is a small number, relatively small number. That's why I do not expect many options. So let's start by just considering different values of z. So let z is 1. Oh, y isn't an integer then. So skip it and let's try z equals 2. Oh, I think it's promising. 6 goes to the other side. 6 divided by 2 is 3. So y is 3. Then I put it to the first equation. The sum is 12, so x is equal to 7. And the next question is about other possibilities. Are there any other possibilities for x, y, z? So let's try z equals 3. No, it doesn't work. Z equals 4. Oh no, y is 0. So we checked all the possible z values and only this z equals 2 works. So this triple says that the number of $1 socks is 7. Yeah, because x is $1 pairs. So 7. X equals 7. Wonderful problem. So I think you will never meet anything like this in a standard school program because this is so rare to say that we have a lack of equations, but we have an additional piece of information that x, y, and z are integers, positive integers. Okay. Let's move on. Oh, it's the same exam, 2015, but problem 22. On June 1, a group of students are standing in rows with 15 students in each row. Okay. On June 2, next day, the same group is standing with all of the students in one long row. On June 3, the same group is standing with just one student in each row. Okay, they are rearranging each time. On June 4, the same group is standing with 6 students in each row. This process continues through June 12 with a different number of students per row each day. Okay, however, on June 13, they cannot find a new way of organizing the students. What is the smallest possible number of students in the group? Okay, idea number one is that each time you rearrange these students, you factorize it. I mean, you represent it as two factors. Imagine the number of students with 20. I don't know. It's a number that has nothing to do with the actual number of students. But if you factorize it like 4 times 5, so 4 is the number of rows and 5 is the number of columns. So it's a factorization of 20. It's not prime factorization, of course. It's just a factorization. It's representing 20 as the product of two factors. But it gives you an arrangement of students with 4 rows. Next time you represent it like, I don't know, 10 times 2. So it's 10 rows, 2 columns. Next time it's 20 times 1, 20 rows, 1 person in each. And now we understand that each arrangement is another factorization. Idea number two, it comes from the problem. It says that there were only 12 such factorizations because on June 13 they couldn't find a new way. Then there must be 12 factors of the number of students. Let's say number of students is n. N is the number of students. So there must be 12 factors of n. So idea number three. So it's a wonderful theorem in the theory of numbers. I don't want to prove it, but look, if a number has a prime factorization of p1 to the power of k1. So p1 is a prime factor and it repeats k1 times. P2 is another prime factor with its own power of k2 and so on. Let's say m, km. If this is a prime factorization of a number, then the number of factors, all different possibilities, including 1 and the number itself, the number of factors can be found by the formula. So you take the power of P1, increase it by 1. You do the same with other powers, Km plus 1, and you multiply all them up. So this is the number of factors. So now we can look at the answer choices. We're looking for the minimum number with 12 factors. Okay, I think it's the most efficient strategy is to start with the middle number. Let's take a look at 60. Its prime factorization is what? 2 squared. Then I have 15, which is 3 times 5. The powers are 1, 1. So what's the number of factors? I increase each power by 1. So 3, 2, 2. It's, oh my God, it's 12. It's 12. So, but I'm not sure it's the smallest number. So maybe 30 and 21. So I have to check them. But I'm pretty skeptical about 30 because it's 2 times smaller than 60. So it's 2, 1, 3, 1, 5, 1. And the number of factors is 2, 2, 2. 2 times 2 times 2, it is 8. Of course it doesn't work. So 21, oh, it's 3 times 7. So I look at the powers and I increase each power by 1. So it's 2 times 2. It's only 4 factors of 21. So of course they do not work. So the least number of students in the group is 60 because 60 has 12 factors or 12 factorizations. So if you are curious about this, I can show you 60 times 1, 30 times 2, 20 times 3, 15 times 4, 12 times 5, and 10 times 6, What is next? 9, 8, oh, 6, 10, and then you can see they repeat. So 60 is, it's 5 times 12, 60 is 4 times 15, 60 is 3 times 20, 60 is 2 times 30, and 60 is 1 times 60. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Oh my God. Oh my God. So only now, after writing down all the possibilities, you appreciate the theorem because it did it so much faster. Yep. Wonderful, wonderful problem. So it's full of ideas, probably new ideas for novices. Yeah, it's amazing experience when you solve problems like that. So see you next time on a new set of problems from AMC. Good luck.